Welcome to Chemical Process Safety. This video is about reading piping and instrumentation diagrams. You might have heard the word P&ID before, but just to make sure we're all on the same page, let's clearly define it. A P&ID is a much more detailed version of a process flow diagram. And actually, this is actually a block flow diagram, even though I call it a process flow diagram. But in a PFD, only process units and process streams are shown, and there are generic icons like boxes and arrows. And in contrast, a P&ID has much more detail using specific icons to mean specific things. So for example, this vessel is a jacketed reactor. There's also valves indicated here. So V2, V4, these are all valves. Pressure relief devices are also shown here. Heat exchangers, and the rest of this video will be basically how to read a diagram that's like this. I want to make the point that both the PFD and the P&ID are important for chemical engineers to know and understand. Obviously, it depends on what you're trying to do. If you're trying to perform a material balance, a P&ID is going to be overwhelming and overkill, and it's potentially going to make things more difficult to understand. Whereas if you're trying to place a pressure relief valve, which is something that we are going to do in a moment, having a P&ID is going to be much more helpful and important because more pipe sections are shown, for example. The type of equipment that you'll see, you should know these icons by heart. So we've got a pump, a flow meter, a vessel, heat exchanger, furnace, agitator or a stirrer, packed column, distillation column, and air-blown cooler. You might see, I mean, some of these may be different. So like distillation column might not have these lines inside of it. But generally, if you see something like this, that's going to be a heat exchanger, for example. The types of valves can be a little bit different. So just a regular manual valve that you would turn by hand is a little bow tie butterfly like this. If it is a control valve, meaning that there's a process control algorithm that automatically opens or closes it, there's a semicircle on the top of the bow tie. A solenoid valve is a special type of control valve that uses an electromagnet that has a couple of rectangles above the bow tie. And a check valve is a one-way valve. So it prevents backflow where the arrow points in the direction of the flow. Different failure modes might also be depicted on a P&ID. So let's say the control valve fails for whatever reason. Does it fail to open or fail to close? And there's different situations where either one of those may be beneficial. So for example, if a pipeline is carrying reagent to a CSTR, continuously stirred tank reactor, you could imagine that obviously you'd want that to fail to close because that would shut down the inflow of material and that would prevent a runaway reaction, for example, or it would prevent the reaction from occurring. However, if there were cooling water going to the jacket of that CSTR, you would want to set that valve to fail to open. So FO and FC signify where that fails. There's also fail locked, which means whatever the last position it's in, it would remain in that position. And then you could also depict that other ways. So arrow pointing up is fail to open, arrow pointing down is fail to close, double-headed arrow is fail locked in last position. The types of reliefs that you'll see, the rupture disc is, I think this looks like an envelope, but I can imagine it kind of looks like a rupture disc that has already been ruptured, kind of from the side view. This is what a rupture disc might actually look like. This is the simplest type of relief valve. It's basically just a sheet of metal. And once it ruptures, that's why it's called rupture disc, it stays open. But this diameter allows material to exit, and that would relieve the pressure so that it doesn't cause an explosion. A more generic pressure relief valve kind of looks like two triangles meeting at the point, and then there's a line here with three lines through it. And a vacuum relief valve is the mirror image of the pressure relief valve. A vacuum relief valve, basically, if there's low pressure inside the vessel, this will open and it'll allow air to flow in, as opposed to the pressure relief valve. There's higher pressure inside the vessel. It'll open and allow stuff out. Let's talk a little bit more about rupture discs. They're oftentimes made out of metal, and they are built and designed to rupture at a certain set pressure. So, for example, 2 atmospheres would be the strength of the metal would rupture. That would be called the set pressure. Try to think to yourself. I know we haven't talked about the alternatives yet, but what are the pros and cons of a rupture disk like this that you can think of? Obviously, because it's so simple, there's no electronics, there's no controllers, there's no connections or anything. It is very reliable, meaning that if the pressure exceeds whatever the set pressure is, it'll just break and that'll be it. It's also relatively cheap because of the lack of the components, and very simple as well. You can change these out relatively easily, so they're made to just kind of slide into place. The downside or the cons is that every time it ruptures, obviously it's broken and you have to replace it. So, if, for example, if your vessel, you expect it to temporarily and intermittently exceed the set pressure, but if that was normal for whatever reason, you would have to replace the rupture disk every time that it exceeded that pressure. Another problem with the rupture disk is once it's open, it'll stay open. And if there's a hazardous component inside, once it's open, that hazardous component will still be kind of leaking out. And in contrast, if the pressure relief valve would open, would allow the pressure to be relieved, and then it would close and reseat itself. The other possible downside of this is that fatigue is possible if there's repeated instances of elevated pressure that doesn't necessarily exceed the set pressure. Okay, the pressure relief valve is a spring-loaded version of this. As I was briefly mentioning this in the last slide, but it'll open, and then once the pressure is relieved, it'll close back again. So again, think to yourself what the pros and cons of this situation may be when you compare it to the pressure relief valve. And obviously, the having it reseat itself is good in terms of reusability. So if the pressure is only exceeded by a little bit, it'll kind of open up and then it'll close right back down again. So there's no need to replace it. These are also adjustable. So with the metal rupture disc, you have to buy whatever set pressure that you want. But you can adjust the set pressure on a pressure relief valve by a lot of these have like little tensioning springs that you can adjust the how the spring will work. These are a little bit more expensive, obviously, a little bit more involved, more specialized pieces of equipment. And you have to worry a lot more about how these are sized as well, because if the size is off, if it's too large or too small, you can get what's called chatter, basically where it opens and closes rapidly. And that's bad for the mechanical integrity of the pressure relief valve. Identification letters. So on a lot of the pieces of equipment, you'll see 2 letters like this. So this is the thermocouple. That is not what TC stands for, even though thermocouple kind of has a TC in it. This means temperature controller. So what do all these letters possibly mean? The first letter can be any one of these. So read through just analysis, flow rate, hand, current level, pressure, quantity, temperature, vibration, position. Or it could be a modifier, differential, ratio, totalizer, or safety. And then the second letter will be the function or the modifier. So TC in the previous slide was temperature control. Let's practice. What does TI stand for? And flipping back, that is temperature indicator. That's basically a thermometer, but a more sophisticated version. TT is a temperature transmitter. LIC is a level indicator and controller, level indicator controller. And FRC is flow ratio controller. LAH, level alarm control. I'm sorry, level alarm high. So if the liquid level in a tank were to rise above a certain set value, that alarm would go off. The line in the middle of the tag denotes the location. So if there's no line, the instrument is mounted in the field near the process. If there's a solid line, it is mounted in the control room and is accessible to the operator. And a dash line means it's mounted out of sight and not accessible by the operator. So I always think this is kind of cool because you can kind of get into the logistics of how these things are built. It's not like the equipment is actually laid out the exact same way as it looks on the PNID. There's connections that you can draw in between some of the equipment. So piping is a thick knot dash line. Process connections are thin lines. Electrical signals are dash lines, and pneumatic signals are kind of these railroad crisscrossy type shapes. So you can see that on this example of a PNID. Again, we've got piping, which is a thick line. Trying to see if we have an example of, we've got a dash line here, which signifies an electrical signal. I thought we had an example of the pneumatic, but that was maybe a different example. So again, the type of line indicates the connection. Notice again how many valves we have. So again, check valve, manual valve, so on and so forth. All right, here's the final boss. So pause the video here and see if you can explain what is going on in either one of these two PNIDs. I probably won't, just for the sake of time, I will not go through the entire example, but maybe I'll put in the description for the video, I'll write a little bit so you can check your understanding. Here's another example that you can do. This is a distillation system. We'll place the relief valves. That's the point of this upcoming module. We haven't gone over this just yet. But once we know how to place the relief valves, we could go through and do that on this PNID. Just more examples here. There's a ton of examples in this slideshow.